And then I'm going to film this so that you can go back to it anytime you need to. So the first passage, what's the first thing we should do when it's data representation? Where should we go? Yeah, the questions. You don't have to waste the time reading the passage, usually ever. So I always skip the passage and go straight to this question. So this one says, the point in figure 1. So figure 1 is where I'm going to look. That's my locator. Labeled C corresponds to the position in diagram 1 labeled what? So I need to look at figure 1 and point C. So figure 1 is like 10 days probably, and a magnitude of 3.2. So 10 days and a magnitude of 3.2. And now I need to go to diagram 1 and see what that means. So, I'm at diagram 1. The magnitude is 3.2. It's probably 10 days, but now I need to know what this diagram means. So it says two stars that are gravitationally bound to each other. If two stars that orbit each other are viewed along a line of sight that is not perpendicular, they will appear to eclipse each other. The orbit of eclipsing binary system Q is shown in diagram 1. So if they eclipse each other, what does that mean? Yeah, so they cover each other. So does that mean the magnitude then would be small or large? So if something is covering another star, is the brightness you're going to see be smallest or largest? Smallest. Yeah, so that's going to be the smallest. Now if I look at my graph, back in figure 1, is this point the brightest or the least bright? Yep, so that means it's going to be in the position where it's eclipsing it, right? Because it's the smallest. So that position is when star 2 is going to be right here, right in front of star 1. So what's the number of that position? Yep. So that's 3. So the answer to number 1 is C. It's not focusing very well. All right. The period of revolution for eclipsing binary star Q. So how long does it take for Q to go around? So if I look here, how many, oh, that one's actually pretty simple. How many days are on this graph? 20. So how many, what's our answer choice here? Yeah, 20. So to get from point A to point A is 20 days. So if I look on the graph here, do you see how it's point A right here? And point A right here? So to get all the way around, that's one revolution. Point A to point A is the distance on this graph. That's 20 days. Okay. The stars in eclipsing binary Q alternately eclipse each other for periods of approximately. So when do they get in front of each other? So, if I look at this one, I know that an eclipse happens around 10 days, but when do they eclipse each other? So, let's look at this one. Okay, so I know that there's an eclipse of star 1 to star 2 in position 3, and star 2 to star 1 in position 1. And then I just need to know what days those happen. So I'm going to go back to my days. This is my light curve. Okay, so one of those is going to be the lowest position because star Q eclipsed, so I know that something is going to happen at point C. And then it's also going to be my brightest portion here. So, point B, I'd say that's probably 5 days. And then point D is probably what? Maybe 13 or 14. So there's this section, 5 to 14 is about 9 days, maybe that's 15-ish. Okay, so then going from here to here, and going from here to here, so this whole distance, okay, so 5 or 4 to 14. But 15's right here. So if I do 13, 14, 15, so this whole period, so that's actually probably closer to 6. So 6 to 14 is 8 days, so that's one cycle, right? And then this 6 to 10 is about 4 days, so it looks like I have 4 days and 8 days. So that's going to make my answer C, because that's the closest. So the whole cycle here from B to D, that's going to be one eclipse rotation of that whole thing. So that's 6 to 14. So that's 8 days as the longest one. So that's when one goes in front of the other. And then if this is 6 to like 10, that's approximately 4 days. So that's looking at our answer choices, we know that 8 days is one of them. And then 4 days is going to be the closest, so that's going to make C happen. Because this is going to be one eclipse. And then this is going to be one eclipse. Because this will be when the star Q, the rotating star Q, is in front of star 1. And then this is going to be the distance it will take from star 2 to head behind star 1 in the graph. Okay, got 3 more questions on this one. So it says the light curves for 2 eclipsing binaries, systems X and Z, are shown. Which of the following hypotheses would best account for deeper primary minimum of system Z? So first off, I don't know what this means, right? But I think I need to know what that one is for this one. So I'm going to look for what that is. The light curve of an eclipsing binary typically shows a deep primary minimum and a shallower secondary minimum. Okay. So, do I need to know anything from here? Nope. So then I'm going to go back here. So, what do I notice about system X? This one's not a very deep minimum, right? The magnitude is about 3.7-ish at 36 hours. But at like between 9 and 12 hours, I have a super deep minimum here. Okay, so system Z has a far more intense light curve than system X. So there's a more extreme difference between the magnitudes of the 2 stars of system X between the 2 stars of system Z. So I don't think that's the case, because which one has a stronger line? Yeah, so Z has a stronger line, so I can cross that one off. Alright, there's a more extreme difference between the magnitudes of the 2 stars of system Z than those between 2 stars of system X. Yeah, I'm going to say yeah. So I'm going to leave that as an option, but I don't know yet because I haven't read all my answer choices. System X has a longer orbital period than does system Z. X is 72 hours. And Z is 21 hours. So that one's true, which means I can cross off J. But now, which one would explain the brightness? Okay? Because I'm looking for a primary minimum. And that primary minimum talks about brightness. So I should be talking about magnitude in my answer, because magnitude is what's equal to brightness. So between G and H, both of these are true, but which one answers the actual question? G. Good. Alright, 5. The greatest total brightness shown on the light curve corresponds to a point in orbit when the bright star is directly in front of the darker star. So I want total brightness. Total brightness is going to be the what and what of the two stars added together.
The light curve?
Yeah, so the brightness, which is measured on the light curve. So the brightness of star 1 plus the brightness of star 2. So should you be able to see, for it to be bigger, should we be able to see both stars or no? Yeah, you should. Because if one is covering the other, you're only going to get the brightness of one star. Right? So you're going to want it where you can see both stars. Because two things are just going to be more than one thing in this one. So the brighter star is directly in front of the darker star. How many brightnesses is that going to give us? It's going to give us 1 or 2 brightnesses? 1. So I can cross off A. The larger star in the binary pair is directly in front of the smaller star. How many brightnesses is that going to give us? 1. So I can cross off B. The smaller star is directly in front of the larger star. How many brightnesses will that give us? It'll give us 1. If it says directly in front, right? It's going to give us 1 brightness. How many brightnesses will answer choice D give us? 2. It says both stars. And also a process of elimination, we cross the other ones out. So the answer to that one is D. Alright, this one. So the passage suggests that the light curve shown in figure 1. What up? Yes. Click to the front of your packet. So sometimes they're going to be a little bit more than 6 questions, so you're going to go by passage, not by 1 through 5. Okay. But this is the last question. Okay. So this thing is so out of focus today. The passage suggests that the light curve shown in figure 1 assumes that the passage in figure 1, by the way, I have my 2 locators here, assumes that the observer is viewing from a line of sight that is not perpendicular to the this is a hard question, to the orbital plane. If the observer were viewing from a line of sight perpendicular to the orbital plane, the light curve of system Q would. Okay, so we're going to go back to figure 1. Now, this says that here's my observer, and he's not perpendicular to the plane. So now what happens if we put my observer here, right, and we put him perpendicular to the plane? What would happen to the light that he's observing from star 1 and star 2 in the system? So, what would happen? So, do we think it would remain unchanged? No, that's like never ever the answer. If it says like not enough info or nothing will happen, then that is the incorrect answer. So that's just a strategy point. If the answer is lazy, then we don't do it. Okay, that's the lazy answer. So, show a larger difference between the primary minimum and the secondary minimum. Maybe. Suggest a longer duration for the eclipses, indicate no difference in magnitude over time. So now, this is where this gets important. So we want to know what the light curve in figure 1 will do. Is this part going to change the number of time the stars take to go around each other? No. Like, just because it's in a different place, the moon doesn't take longer to go around the earth doesn't take longer to go around the sun. So this part is going to remain unchanged. Okay. Now what about this one? Is the star's brightness itself going to change? Like if I'm standing in a different place, did the magnitude of that star change? No. So this one is actually kind of a common sense question, not a sciencey question. So show a larger difference between the primary minimum and the secondary minimum? No, because we said the magnitude of that isn't going to change. Select a longer duration for the eclipses. Is the period going to change? Is that x-axis going to change? No. So my answer here is J. So it's actually not going to change the magnitude, right? It's just going to change what the observer sees. If the observer stands in a different place, the observer will see something different, but that's not going to change the star itself. However, it's not going to remain unchanged from figure 1, okay, because figure 1 is right here. It is the surface brightness from where it's observed. So it's not going to change what the stars are doing, but it is going to change the brightness. We just don't know what direction because we don't know where the observer is actually going to be. So we have to say no change in magnitude, but it might just look like a different curve. Questions there? Okay, so